Hello, good day to each and everyone. In this video, we will be dealing with geometric optics. Now we will divide this lesson into three parts. For our first video, we will be dealing with the ray model of light as well as the image formations in mirrors. In the second video, we will talk about mirror equation and magnification equation. While on the last video, we are going to deal with the Snell's law of refraction as well as the different image formations in lenses. So without further ado, let us start with this lesson. In our previous lessons that we had in our course, we dealt with oscillations and vibrations, and we also dealt with sound waves. Now, in this lesson, we are going to deal with light as a form of a wave. Now, we will not be dealing with the other aspects of light because, as we all know, light is both a wave and a particle. But in this lesson, we will be dealing with the wave nature of light. So in order for us to start with our discussion, allow me to switch with my presentation for this lesson. So the source of this information is that I got this from Giancoli Physics of the 7th edition. So we are going to deal now with our lesson for this video. To somewhat show you the contents of this lesson, allow me to flash this to you. Please, you may as well welcome yourselves to read our coverage for this lesson. Okay, and we are also going to deal with these topics in our next slide. Now that we have a clear overview of what we are going to deal with this topic, let us first deal with the very basic question, one that somewhat triggers our interest with light. What is light then? We know already that from our previous discussions that light is a form of an electromagnetic wave, right? Now, what is then an electromagnetic wave? So, an electromagnetic wave is simply a transverse wave, which we know we have dealt this with our previous discussions, right? So, a transverse wave may be imagined somewhat as this. You tie one end of the rope on one end, and then you set its motion up and down, and you will notice that this vibration oscillates in the direction parallel to the motion of the production of this wave. And we know that in molecular level, the ones that are vibrating are your atoms. As it jumps from one energy level to another, it releases this electromagnetic wave pattern in a form of alternating electric fields and magnetic field. And it's because of these oscillations that happens in the vibrations of your atom, it is said and it is known that an EM wave can travel without a medium, or it can travel through empty spaces, and that it's very fast. It travels around 3 × 10⁸ meters per second. And in fact, it's not only light that is an EM wave. In fact, they are everywhere. We see them through our phones, in a microwave oven, televisions, even our Wi-Fi, as well as your Bluetooth devices utilizes EM waves. We also have some X-rays used in medical diagnostics, radiotherapy, and even collecting observations from distant galaxies. Even our sun emits an EM wave, and light itself is a form of an EM wave. So therefore, we can say that EM waves are actually everywhere. So we are actually surfing in this sea of EM waves every day. And that, in fact, there are many of them. And we know them, we studied them from our previous courses. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, to name a few. And visible light, or light itself, is just one of this grand array of spectrum of your EM wave. So we will deal with light rays in particular. Now, to study about light as a wave, an electromagnetic wave, we have to deal with the ray model of light in order to simplify our understanding. Now, light often travels in straight lines. We represent these straight lines using a ray, which are straight lines emanating from an object. This is an idealization, but it's very useful in geometric optics, especially that we have to use geometry in order for us to understand how light behaves. So we use this concept of reflection in order for us to understand how images are formed in mirrors. Now let's talk about plane mirrors. Now, a plane mirror is a smooth surface, okay? And that in a plane mirror, we observe what you call as the law of reflection. Now, a law of reflection states that the angle of incidence as well as the angle of reflection are equal to each other. That means that at which angle light rays enter the mirror, the reflected rays should also be reflected at the same angle as that it hits from the mirror. And usually we use that imaginary line that runs vertically from the surface of the mirror. We call that as the normal line as our reference when we measure angles to which the incident ray and the reflected rays leave the mirror. Okay, so that's how we are going to utilize that one. Now, there are two types of reflection. Now, number one is the diffuse reflection. Now, diffuse reflection usually happens in rough surfaces. When I say rough surfaces, that means the surface is uneven. Now, in a rough surface, diffuse reflection is much common. And in fact, law of reflection still holds, even if it's a rough surface. It's just that there are many incident rays, or that the incident rays varies because of the unevenness of the surface. And this is in fact the main reason why we are able to see different shapes, different lines, even the depth of a certain object. We can observe it because of diffuse reflection. And that's the reason why you can read things, why you can see the shapes of any objects that you see around you, and that is due to diffuse reflection. Now, another type of reflection which is very much common in mirrors is what you call a specular reflection. In specular reflection, it happens in smooth surfaces like mirrors, plane mirrors in particular, or even spherical mirrors. So in specular reflection is much different with diffuse reflection. So how do they differ? Now, in diffuse reflection, it's like this. You see your eyes reflected, your eye sees rather, that all reflected rays can be observed at all angles. But in specular reflection from a mirror, for example, your eye must be in the correct position in order for you to see that object exactly hitting the mirror. So like for example, if you want to see an object from a mirror, you must position yourself exactly at the same angle as the object is positioned from the mirror so that you can see its reflection from the mirror. So that's how specular reflection happens. Okay, so the reflection of images in plane mirrors is very much common in general because we use plane mirrors every day, and that we often observe these image characteristics in plane mirrors. That is, the image is virtual. That means it's as if the image is just there inside the mirror or behind the mirror, and it has the same size as the object, and it's laterally reversed. So there's one characteristic that you should not forget in a plane mirror, is that the object's distance is as if the same as that of the it should be the other way around. The image distance from the mirror is the same as that of the object's distance from the mirror. Okay, and that it's laterally reversed. So what do you mean by that? Now, when we speak of laterally reversed, that means that if you raise your right hand, your reflection is actually raising its left hand. Or we call this in general as lateral inversion. That's how we observe that. Now, I want to show you this example. So, sorry, I made a scribble of this problem a while ago, but allow me to please erase this so that you will not be confused. So, let's have this first problem. Let's say two plane mirrors make a right angle of 30 degrees with each other. A light ray enters the system and is reflected once off of each mirror. Now, the question here is, through what angle is the ray turned? Oh, this is a very interesting problem. Now, in order to simplify our understanding about how to answer this problem, this actually requires us to vividly visualize how light rays behave when they hit the surface of a plane mirror, as well as our understanding of the laws of reflection. So allow me to draw how this problem should be drawn. So let's just say, for example, please forgive me if my drawing is not that accurate. So let's say I have here plane mirror number 1, and this is plane mirror number 2. Allow me to label this as number 1, and this is number 2, so that it will signify that these are our two mirrors. Now, according to this problem, the mirror is actually the two mirrors are actually positioned 30 degrees from each other. So here, let's just say 30 degrees. Okay. So that's how the problem looks like. Now, according to this problem, a light ray enters the system and is reflected once off of each mirror. Now, it doesn't say much about at which angle the light ray enter the mirror. So that means that we have to assume certain position. Okay, so I'm going to somewhat assume, class, that let's just say let me change the ink color. Let's just say that the ray of light enters mirror number 1 horizontally. Okay, let's draw that horizontally. Okay, now this is the ray of light. I'm going to call this ray, let's say, L. Okay, ray L. Now, as it enters this light ray, how do you know at which angle should it leave the mirror number 1 before it hits mirror number 2? So it should be like this. Okay, so allow me to extend some light rays here. Okay, sorry, the surface of the mirror rather, so that we can cater on more distances. Okay, there. Now, what I want to do, class, is that I would like to draw how do you call this? An imaginary line. Okay, so I'm going to draw an imaginary horizontal line here. Okay, there. There. Okay. Oops, sorry. It should be like this. So allow me to erase first. Okay. If we are going to imagine, so since that is a horizontal line, for example, you're going to imagine this. We imagine a transversal. We need to have a good understanding of background of geometry for this case. So that means that since this is, if we are going to imagine this as a transversal, I'm going to draw a straight line here, and also a straight line here. You will notice that this angle here should also be 30 degrees, right? Okay, that should be 30 degrees. Now, if we are going to somewhat, how do you call this? How am I going to call this? A normal line. Let's just say that this is a normal line for this ray here. So this is a normal line, so that means that this angle here should be 90 degrees from each other. So this should be 90 degrees from each other. So knowing that this is 30 degrees here, then that means that this angle here must be 60 degrees here. So that means that this angle from this side here should be 60 degrees. And now the question here asks us through what angle is the ray turned. So technically, the angle is actually turning from here at exactly 60 degrees. Okay, so the answer for this problem is actually 60 degrees. So this is how we tackle this problem. So I hope that you understand that one. So let's move on to another problem. A person jogs towards a plane mirror at a speed of 3 meters per second. How fast is he approaching his image in the mirror? Now this is not much difficult. It's very easy to understand. Let's just imagine that we have a mirror here. Okay, this is your mirror. Let me just label it. Now, a person jogs towards the plane mirror at a speed of 3 meters per second. So this person is running towards the mirror at a speed of around 3 meters per second. Now, according to the question, how fast is he approaching his image from the mirror? Now, you might be thinking that since it's law of reflection, then the answer should still be 3 meters per second, right? Because after all, if this man sees his image here, okay, it should be running 3 meters per second. But you have to take note that motion is relative, right? It's relative from one another. Now let's just say that if his image observes the actual object running to the mirror at 3 meters per second, you have to take note that this image is also moving at 3 meters per second, right? So therefore, since they are approaching from each other, so what will be the perceived speed of that image as this person approaches towards the mirror, right? So that means that we have to add up 3 meters per second plus 3 meters per second, and 3 meters per second. So that means that the relative speed for that one should be around 6 meters per second. That's how fast this person seems to be approaching from the mirror. Okay, so that's how we are going to solve this problem. Now let's move on. Now, another type of mirror that I would like to somewhat talk about is spherical mirrors. Now, for spherical mirrors are a kind of mirror with a curved reflecting surface. Now, both inner and outer surface the mirror can also reflect light. Now, there are two types of spherical mirrors depending on which surface you would like to reflect light rays from. Spherical mirrors are shaped like sections of a sphere and may be reflective on either the inside, which we call as the concave, or outside, which is the convex. Now, mind you, the laws of reflections are still involved in spherical mirrors. It's just that depending on which angle or which surface the light rays enter incidentally to the spherical mirror, the reflection happens differently. Okay, so characteristics. So what are the main characteristics? So for concave mirrors, they are called as converging mirrors because they focus light rays, and that the image formed varies with the object's distance from the mirror, and that the image can be small or large, or it could be real or virtual. Now, for convex, they are called as diverging mirrors because they diverge light rays, and that image formed is always smaller compared to the object. Now, in describing images, you usually use the ray diagram method. So what is a ray diagram method? Well, it's a very convenient process wherein we can approximately predict or describe the image characteristics that are formed in spherical mirrors. So it's a diagram that usually traces the path that light takes in order for a person to view a point on the image of an object. Now, in a ray diagram, before we deal with this rather not that difficult process, let's first identify some key terminologies here. Okay, so let's have some parts of the spherical mirror. So I labeled them according to their parts. Now let's talk about point P. We will call this your principal axis. This is an imaginary line from the center of your mirror. Now for the vertex V, this is our center of our spherical mirror. Well, center of curvature is the center of the sphere in which the mirror forms a section. So how do we understand that? So let's just imagine that that curved reflective surface was once part of a mirror or once part of a sphere. Okay, so if you're going to complete that section, that point C there is our center of our sphere or the center of the circle itself. Okay, next we have the radius of curvature. Now the radius of curvature is the distance between the vertex and the center of curvature. So technically it's just like the radius of the circle. Okay, while the focal point or F, we also call this as our principal focus or the focus of our mirror, the point in which all reflected rays seem to meet, and the focal length, which is the half the distance of the center of curvature. Shall we say this is the distance between the focal point as well as the vertex of your mirror. Okay, so now if we observe rays coming from a very far away object, we will see that these rays are actually effectively parallel when it hits the surface of our spherical mirror, whether it's a concave or a convex mirror. These rays strike the mirror and they are essentially parallel. Now, parallel rays striking a spherical mirror do not at all converge at exactly the same place if the curvature of the mirror is large. Right? Let's just imagine that the mirror is very, very curved and that all parallel rays enter that mirror. Well, of course, because of the shape of the mirror itself, because of its large curvature, you will not observe all light rays that are parallel hit or converge at exactly the same point. So they will always converge at different points. Now, this is what you call as spherical aberration. Now, if the curvature is small though, the focus is much more precise, and that the focal point is where the rays converge. So as you can see, if we can do if we can make the focal point, or not the focal point, the curvature of the mirror itself very small, then we will observe that the focus would be more precise. So that's why the focal point now is where the rays converge. Okay, so now using geometry, we find that the focal length is half the radius of the curvature, or in formulas, F is equal to R over 2. And that this phenomenon of spherical aberration can be avoided by using parabolic reflectors. These are more difficult and expensive to make, and so are used only when necessary, such as in research telescopes. So I think parabolic reflectors are not that common terminologically, but maybe you have seen this used in your antennas, like for example in cables. See those circular thing that acts as a reflector of signal? It's actually a parabolic reflector. And also in telescopes, with disc satellite dishes, those are actually parabolic reflectors. Now, making this makes it a bit expensive. That's why they are only used when necessary. So, like in research telescopes and so on, right? So, how do we describe images in spherical mirrors? I would like to use this acronym LOST, or LOST method. So L stands for location. So where the image is formed, location is where the image is formed. Usually we use the points F and C as reference, or the focal point and the center curvature as reference for this. Now orientation, inverted if it's upside down image, upright if it's an erect image or it has the same orientation as that of the object. Now S is the magnification. Enlarged if it's bigger than the object, reduced if it's smaller than the object, and equal if it has the same size as that of the object. And usually, magnification is solved using a particular formula, which we will be discussing in the next video. Well, technically, we can describe magnification with this reference, m is equal to 1. Now, if m is equal to 1, that means that the image is equal to the size of the object. But if m is greater than 1, then that means that the image is actually larger than the object. But if m is less than 1, then that means that the image is actually smaller than the size of the object. So we will discuss that more in detail in our next video. Now, how about T, type of image? So when you say type of image, we can only have two types. We have real image and we also have virtual images. So when we speak of real images, they are inverted image formed when the light rays meet at a particular point after reflection from the mirror. Now, real images are inverted images, meaning to say they don't have the same orientation as that of the object. So if an image is inverted, then that means that the image is a real one. Okay, and that what's amazing about real images is that you can always project them on a screen. Okay, like in the projectors. So, and in virtual images, these are upright images formed only when light rays appear to meet at a definite point after reflection from a mirror. So a virtual image is always an upright image. They are formed as if they seem to appear behind the mirror. Okay, so that's how virtual images are described. Now, how do we describe images right now that are formed by spherical mirrors? So let's use the rules for ray diagram in order for us to understand how light rays behave in concave mirrors. So let's first use concave mirrors in this example. So let's first, number one, light rays that leave the object, which is the upward arrow here, are reflected, or they leave parallel to the principal axis, which are reflected and pass through focus, or our F. So how do we apply that? First, draw that parallel ray from the tip of your object, which is our upward arrow here. Then once it strikes the mirror, according to the rule, it is reflected passing through the focus, or F. So this is now our rule number 1. Okay? Now, for number 2, light rays pass through F and are reflected parallel to the principal axis. Now, according to this rule, the light rays pass through F from the object and is reflected. Once it strikes the mirror, it is reflected parallel to the principal axis. This is our rule number 2. Rule number 3, light rays pass through the vertex V will strike the mirror at the same angle as that of the incident ray. This is what you call as the law of reflection, right? So, as you can see, we assume that that green light ray there enters and leaves the mirror at the same angle from the principal axis. So, if we are going to combine all those rules, there, you will see that all these 3 light rays, which are the dashed lines, that those are the reflected light rays, they intersect at a certain point, which is there. This is our image now. And how do we describe this image? So it's between F and C. That is our location. As you can see there, inverted, because how do I know it's inverted? If you see, the intersection of the reflected rays happens somewhat below the principal axis, and if you're going to check, our object is upright from the principal axis, right? Now, the object is upright, but the intersection happens below the principal axis, so that means that our image is actually inverted in this case. It is reduced. How do I know it's reduced? Well, if you look at the relative size of the arrow based from its height, you will see that the blue arrow is shorter than the the black arrow. Okay, and how do I know it's a real image? Now it's because all inverted images are real images. So this completes our image description from this example. Now, for concave mirrors, though, image description varies with the object position from the mirror. Okay, so as you can see here, if you are too near from the concave mirror, the image gets bigger, and if you are at a certain distance from the concave mirror, you might appear inverted as well. Okay, now how about for convex mirrors? Now, for convex mirrors, the rules are still the same. Okay, we still apply the same rules, but we just interpret it differently. Parallel rays of light from the object upward arrow are reflected so that they appear to come from F behind the mirror. So these are the reflected light rays. This is the incident ray rather. Then, as you can see, I draw a red dashed arrow to indicate that as if the object is passing through the focus of your mirror. But actually what happens is that it is reflected away from the mirror. It's diverging. That's why it's called diverging mirror. That we just draw that imaginary line so that we know that the light rays are actually passing through the focus of your mirror. Now for general rule number 2, a ray directed towards the focal point is reflected parallel to the principal axis. So as you can see, I draw a thin blue arrow to indicate that the light ray leaving the object is seemingly passing through the focus, but actually what happens is that it is reflected parallel to the principal axis, and we just extended that line towards the inside of the mirror so that we will observe what happens after all these three rules are applied. And for the general rule number 3, light rays that pass through the vertex is reflected at the same angle as the incident ray. There. Extend. Now, if we combine all these three rules, you will see that the reflection of the intersection of those reflected rays happens at that particular point, and that indicates our image formation for convex mirrors. Okay. Now the image formation here, how do we describe this? Behind the mirror, because it's as if the image is at the back of the mirror. Upright, because you can see the intersection happens above the principal axis, which is now having the same orientation as that of the object. Reduced, well, it's because the arrow is much shorter compared to the object. And it's virtual because all upright images are virtual images. And that there are many applications of these image formations. So we have, let's say for example, for convex mirrors, rear view mirror for car vehicles, or shop security mirrors like the ones that you see in many convenience stores, right? And even blind curve mirrors or traffic mirrors. So the use of that is that convex mirrors covers a wide view so that you can see everything behind it. Now for concave mirrors, let's say headlights of your car vehicles, that's why it shines brightly, because it has concave reflectors in them. Okay, telescopes, and even your dental mirrors. So there are a lot of things that you can still imagine of its uses. So I leave that to your hands. And all in all, those are all the things that I would like you to somewhat have for this lesson, for this video. So we will stop from here, and that we are going to discuss the next part of this lesson in our next video. So to summarize everything that we have discussed so far, ray model of light is very much useful when we have to understand the behavior of light, especially when we deal with the image characteristics in mirrors. So in this lesson, we just talked about how light behaves as a wave as it reflects from the surface of a plane mirror and spherical mirror. So in our next video, we'll be dealing with the mirror equation as well as the magnification equation. So stop from here. Thank you so much for listening to our lesson. So see you next time in our next video for this lesson. Bye, and I hope that you had a wonderful learning for this video.